Here's 1 minus the square root of x. Again, this is a constantly decreasing function. Now notice that the domain of this function is closed on the left end, 0 to infinity. So since it's starting here at 0 and is continuously decreasing, and 0 is included in the domain, this left endpoint is the absolute maximum. The absolute maximum occurs at 1, where x is 0. So notice that that where x is 0 is a critical value, because if we take the derivative of f, we see that it's not defined at x equals 0. The next example, find the critical numbers of this function. So the critical numbers are where the derivative is 0 or not defined. So we take the derivative. We see that that's defined everywhere. So we find where it's equal to 0. We solve this equation, and we see that the solution is when theta equals n pi, where n's an integer. So the derivative is 0 at n pi. So those are the critical numbers of this function. In example 7, we're supposed to find the maximum, absolute maximum, and absolute minimum values of this function. So notice that this is really telling us to use the extreme value theorem. We're finding absolute max and mins, and we have a closed interval. So we can, and this is a continuous function on that interval, so we can use the extreme value theorem. So we're first going to find the critical numbers and evaluate the function there. We'll evaluate the function at the endpoints, and then we'll compare them. So we find the derivative. We're going to use the product rule. So I find that derivative, and notice that it's defined everywhere on this interval that we're interested in. So then we set that derivative equal to 0 and solve it. So I factored out 1 over x cubed, and notice that that factor is never 0. So that means that this solution occurs where this factor is 0. If we solve that, we get x equals e to the 1/2 power, which is about 1.649. So we have our critical number. Now we evaluate the function at the endpoints. And then we put them all together and compare. So we can see that at the critical number e to the 1/2, the function value is the highest. And at the endpoint 1/2, the function value is the lowest. So summarizing all this, remember that a local max or min can be an absolute max or min, and local max and mins cannot occur at endpoints. The extreme value theorem guarantees us that we have an absolute max or min on a closed interval if our function's continuous. Fermat's theorem tells us about critical numbers, and that if we have a local max or min, it's going to be at a critical number. And then we have this closed interval method, which is what we use to find absolute extrema of a function on a closed interval.